Last class I have discussed about AC to AC converter with resistive load. There we have seen that problem of DC component which was there with one thyristor and one diode was resolved in AC to AC converter with two thyristors connected in anti-parallel. Today I will discuss about two thyristor connected in anti-parallel across a inductive load. As most of the loads are inductive in nature, so it is important to understand the behavior of converter with inductive load. So let's start. Here you can see that two thyristors are connected in anti-parallel. Thyristor number 1 will conduct in positive half cycle of the input voltage and 2 in the negative half cycle. At the same time, this source current is equal to load current. Now the problem is that here instead of resistive load, RL load is connected and the load is highly inductive. So we know that across the inductor when current increases, then polarity is here positive, here negative. So the positive voltage is developed across the inductor. Now when the current reduces because of the reduction in AC input voltage, polarity of the inductor reverses. So here it will be negative, here it will be positive. Then what will happen? This voltage will add up with this source voltage. Then even in the negative half cycle, we can see that thyristor number 1 continue to be on because the net voltage, this VL and the source voltage becomes positive. So anode voltage is more than the cathode voltage. That means favorable condition in the negative half cycle also we will see for this thyristor number 1. Likewise, we will see the favorable condition for thyristor number 2. So let's analyze this circuit. And this circuit is very important because most of the loads are inductive in nature. So we have to understand the behavior of this circuit. So let's start this. Let's assume that thyristor number 1 is triggered at alpha. And due to highly inductive load, the thyristor 1 will not be off at pi. As I told you that after pi also thyristor 1 will continue to conduct. It will continue to conduct till current becomes 0 and the angle at which this current becomes 0 is assumed as beta. And this angle is also known as extinction angle of thyristor. Then conduction angle of thyristor is beta minus alpha because at beta thyristor is turned off and alpha thyristor is turned on. So the conduction angle of thyristor number 1 is beta minus alpha. And the beta depends upon the power factor angle of the load phi. In case of resistive load, that was unity. So at pi thyristor turns off, but here it will not be turned off at pi. Some extra conduction of thyristor we will see. Let's take the input voltage is Vm sin theta. As it is a series connection, so the source current is equal to load current and assume it as I. So applying KVL, this LDI dt plus I into R is equal to supply voltage. So here you can see LDI dt plus IR is equal to Vm sin theta. This I will be small I, this one. Then solving this equation number 1, we will get this current I is equal to Vm by impedance of the circuit, and this is square root of R square plus omega R square. Omega is the frequency, 2 pi f. Sine of theta minus phi. Phi is the power factor angle. Power factor angle of this load RL. In case of resistive load, it was 0, unity power factor, plus k into e to the power minus r by r into t. Now this constant K we will find based on initial condition, and that is at theta equal to alpha we are triggering our thyristor number 1, and from that point current starts building. So you can assume that at theta equal to alpha current is 0. So just put I equal to 0 here, you will get the value of K, and that K is equal to minus of Vm by root under R square plus omega L whole square sine of alpha minus phi e to the power R by L into alpha by omega. Here theta is equal to omega t is equal to alpha. So t is equal to alpha by omega. So just this one. Then from equation number 2 and 3, we can find net instantaneous current flowing through the circuit, and that is equal to Vm by root under R square plus omega square L square sine of theta minus phi minus of sine of alpha minus phi e to the power R by L alpha by omega minus t. Just substituting the value of K at this point, you will get this current I. Now let's analyze the waveform of this circuit. What will happen when at alpha we will trigger the thyristor number 1, then the thyristor number 1 will be turned off at beta, then again the thyristor number 2 is triggered at pi plus alpha. Let's see the waveform. Here you can see this is our input AC voltage, purely sinusoidal input voltage we have given across the circuit. Now this is gate pulse for thyristor number 1, it is at alpha. Then again it is coming at 2 pi plus alpha. So in the positive half cycle, this thyristor number 1 is triggered. Again in the positive half cycle, thyristor number 1 is triggered. This is the reference line. And in the negative half cycle, thyristor number 2 is triggered at pi plus alpha. So this angle is alpha, this point is pi, and this point is pi plus alpha. So likewise, switching pulses are given to this thyristor number 1 and thyristor number 2, and the input voltage is sinusoidal. Let's see what kind of output voltage waveform and current waveform we will get in case of highly inductive load. So this one is our same input voltage, positive half cycle, then negative half cycle. Thyristor number 1 is triggered at alpha, thyristor number 2 is triggered at pi plus alpha. So this point is alpha. So you will see that output voltage we are getting from alpha, and it will follow the input voltage. As you can see, whenever either of these switch 1 or 2 is on, this output voltage becomes parallel to the input voltage. So the output voltage will follow the input voltage pattern. So here the voltage is like this. This is equal to your input voltage. Now at beta, thyristor number 1 is off, because at this point the current becomes 0. That means inductor is now completely discharged. So this is discontinuous conduction mode of operation, because for some duration of time our load current is 0. So you can see here from alpha the current starts increasing. Now after reaching peak value, this current will reduce. So during this period, voltage of the inductor reverses, and this voltage will be added up with this voltage, and you will see net voltage across the thyristor. After pi also you will get positive voltage, so thyristor will continue to conduct after pi also. So this is the reason behind it, and we have discussed these things in detail in single phase rectifier also. So after pi we are getting this current, so thyristor number 1 is on. So 1 is off at beta. So this is known as extinction angle of thyristor number 1. Now from beta to this point, pi plus alpha, Now the negative half cycle is started from here. So from pi plus alpha, output voltage will follow the negative voltage pattern. So this voltage you will see till thyristor number 2 is on, and the thyristor number 2 will also be on more than 2 pi. Here you can see this is the point 2 pi. So after this also you are getting this output voltage because thyristor is still conducting and thyristor number 2 is off at this point. This point is your 2 pi plus beta. So this point is 2 pi and this is 2 pi plus beta. So thyristor number 1 is off at beta and 2 is off at 2 pi plus beta. That's why you are getting this output voltage and the current is now 0. So the positive current you are getting because of thyristor number 1 and the negative current because of the thyristor number 2. Then again at 2 pi plus alpha, thyristor number 1 is triggered. Then the same cycle will be repeated and you will get the output voltage following the input voltage. Let's see the zoomed version of the same waveform. So here it is your 0 to pi, then it is your pi to 2 pi, then 2 pi to 3 pi, like this. In the positive half cycle, you can see the output voltage. Here it starts from here. In the positive half cycle, this is the point alpha. From alpha to this point is beta. So this output voltage is this one. So during this duration, this output voltage is following this input voltage. Then at this point, this is your pi plus alpha. So at pi plus alpha, thyristor number 2 is triggered and the current starts in the opposite direction from pi plus alpha to 2 pi plus beta. So this point is 2 pi plus beta. And during that duration, the load is connected with the source. So the load voltage or the output voltage will follow the input voltage. So you can see the exactly same waveform you are getting across the output voltage. This one. Then again from this point the cycle will repeat. You can see the positive half cycle is exactly equal to the negative half cycle. So here also you will see the average output voltage will be equal to 0. And this extra conduction from pi to pi plus beta you are getting because the inductor reverses its polarity and supports the input voltage to give extra conduction to thyristor number 1 and here extra conduction to thyristor number 2. So this is the basic property of inductor. Because of this one, the extended period output voltage we are getting. In case of resistance, you have seen that at pi the thyristor number 1 turns off and it turns on again at this point, and from this to this point the voltage was 0. So if the load is more inductive, then you can see this extended period will increase. So you can say that for more inductive load, if the firing angle is more, then output voltage you can get, it will be shifted right hand side. And to get symmetrical output voltage, to obtain average output voltage 0, we have to fire the thyristor symmetrically. That means if one is triggered at alpha, then second one should trigger at pi plus alpha, and it should be ensured that before turning off of thyristor number 1, 2 should not be fired. Otherwise, unwanted behavior of the circuit you will see, and the lots of ripple across the output voltage and harmonics will increase. So here it is, current is 0, here also current is 0. So during this period both the thyristors are off. Here also it is off. So here thyristor number 1 is off and here thyristor number 2 is off. Let's find the commutation angle or the extinction angle of the thyristor beta. So this point beta we have to find now. Now you can see from here at theta is equal to alpha, this point current is 0. At the same time at theta is equal to beta, current is 0. So we will take help of this I equal to 0 to find this beta. The angle beta extinction angle can be found from the condition theta is equal to beta and I equal to 0. You can see here this equation. Just put I equal to 0 and theta is equal to beta. You will get that expression. So sin beta minus phi is equal to sin alpha minus phi e to the power r by L alpha minus beta by omega. So this will be equation number 4. Based on that one, if you know the other parameters, that means phi, alpha, r, L, omega, then you can find the value of this beta. Now to find the RMS output voltage, let's see here the waveform. Alpha to beta, it is Vm sin theta. Then similar waveform here we are getting. So we can obtain RMS output voltage for one pulse and multiply it by 2. See. So RMS output voltage here you have to multiply it by 2, then 2 pi alpha to beta Vm square sin theta square d theta, and finally you will get Vm by root 2 square root of beta minus alpha plus sin 2 alpha by 2 minus sin 2 beta by 2 divided by pi. Now to find the RMS thyristor current, that means through each thyristor how much current will flow. So you can see here the current through the thyristor number 1 is alpha to beta. See, this is waveform alpha to beta, and the current expression already we have got from equation number 4. So let's see. So it is 1 by 2 pi alpha to beta I square into d theta, and the RMS output current, it is summation of the two currents. You can say square root of current through the thyristor number 1 square plus current through the thyristor number 2 square, the RMS currents of the two thyristors. Here we have to take, and you will get a square root of 2 into RMS current of each thyristor. Then to find the average value of the thyristor current, simply you just use 1 by 2 pi alpha to pi I d theta. You will get the average value of the thyristor current. Now one thing is important to discuss here, that in case of resistive load, shorter pulses we have applied to turn on the thyristor number 1 and 2, but here we have to apply larger pulses across thyristor number 1 and 2 till favorable condition is there to turn on the thyristor number 1 and thyristor number 2, and this is because of the inductive effect of the load. So today we have discussed about AC to AC converter based on inductive load, and here we have seen that extra conduction period of thyristor number 1 as well as thyristor number 2 we have got because at the time of discharging current, voltage across the inductor reverses, and that voltage adds up with the source voltage to give positive voltage across the thyristor number 1 as well as thyristor number 2. So extra conduction of these thyristors we will get if the load is inductive. Then we have found out the RMS output voltage, average output voltage, RMS thyristor current, and RMS output current. From next class we will see some other topic of this power electronics subject. Thank you.